Hello, welcome back to CSC 263 Database Management Systems at Adelphi University. In the previous video, I introduced the concept of normalizing data as a method to remove redundancies from the data, and the idea for removing redundancies came from the need to increase data integrity by eliminating unnecessary redundancy from the database. We did that through a process called lossless decomposition. Now let's take a look and see how that process actually works. So from the beginning, we have to realize that we analyze our database schema one relation at a time. We don't consider the entire schema for normalization. We consider individual relations to be normalized. So let's start at the beginning. Unnormalized form, which doesn't really exist, but for our purposes, we're going to say unless we've demonstrated that a relation is in a higher form of normalization, we're going to assume that it is not normalized at all and that it is therefore in the unnormalized form. So basically, until proven a higher level of normalization, something is unnormalized. The normal forms, at least the first three that we look at, are numbered, with the first normal form being the lowest form of normalization and the third normal form the highest. The normal forms build on each other, which means that if something is in the second normal form, by definition it will be in the first. Likewise, if something is in the third normal form, it will be in the second and in the first, transitively. So let's take a look at what the first normal form means. Relational databases typically do not allow the use multi-valued attributes. So in other words, each attribute value should be singular, atomic. And that is what the first normal form is all about. A relationship is in the first normal form if and only if all attributes are defined on atomic domains and each attribute value contains only the single value. So it's a composition of two. It puts requirements on the domain and it puts requirements on the values stored in the database. Our domain integrity rule already told us that we have to define domains for all of our attributes. What 1NF adds to that is that those domains have to be atomic. Let's take a look at it. So for example, if I want to store someone's home address in a database, I could create a field for home address and let people type the full address in there. But that does not accommodate then for the fact that I might want to break down the address in, say, a street, a town, a state, and a country, or maybe even a zip code. Because the domain is atomic, it would make no sense to talk about subdividing that home address into multiple subfields. I could probably do some string matching, but that's different. The database schema represents some semantic knowledge, meaningful knowledge on the domain. And so that's why we'll often see the database being split out into street, town, state, zip code, country. These are all then smaller domains that are atomic. Now, sometimes it is a discussion that you need to have. For example, if we are talking about a date of birth. Now, the date of birth is a singular entity. It is a combination of year, month, and day. You could say, well, that's not atomic because I could split it up into a year, a month, and a day and record, year of birth, month of birth, and day of birth. You're absolutely right. You could do that. Now, the question then is, why would you? Are you ever going to do this? That it is absolutely necessary for you to do that. And so this is one of the first places where we'll see that database design has some intuitive component to it as well. If it makes sense to consider the date of birth as a unit, then keep it as a unit. But if it would make sense to say, I want to run reports on everyone in January, then maybe you do want to split this out. It really depends on the system that you're building and the domain for which you are building that system. But either way, in the first normal form, you have to make those decisions. Look at your domains, see if they can be made into atomic domains. Once that is done, we're going to look at the values, and we're going to make sure that each tuple and each attribute in a tuple only contains one value at a time. Relational databases are not multi-valued. If they're not, we have to take care of that. If they are, we're good to go. So the opposite of this, of course, is a relation would not be in first normal form, and so that means that we need to fix it. So we have identified an anomaly. We have either identified a non-atomic domain, or we have identified a tuple that contains multiple values in a single attribute. If that domain is non-atomic, we have to redefine it, and we have to figure out how all of those non-atomic domains can be split up into atomic domains, and then we have to update all of our data to match. And so that could be a fairly extensive process. Same thing for a relation that has multiple values in a single cell. In that case, I would have to copy each tuple multiple times, but only contain one value in there. So copy the row as many times as you have values, populate each row with only one of these values. Let's take a look at an example. I might have a relation here that has a name, a course, a term, and a grade. And it's based on the student. So for example, here I am, Kees Leune, and I have received grades for CSC 263 databases and Math 423, which is something hard. But notice that there is no line, horizontal line, between the courses or between the terms or the grades, and that signifies, in this case, that that is in multi-value. So if I start looking at this, I have a whole bunch of problems. First of all, name is not an atomic field. I can split that up in first name and last name. Course is not either. I have a course ID and a course name, so I need to split that up too. Term, however, is. Fall 2019 is a comprehensive term. I'm not going to split that up in fall and then in 2019. It's one term. And the grade as well. So if I'm just looking at my domains and my domain knowledge, I'm going to have to split up name in first name, last name, course in course ID, course name, and term and grade I can leave as is. When I look at the multi-valued nature here, I can see that I have two courses with grades in a particular term for a single row. Can't do that either. So for the second entry, I'm going to have to copy all of the fields that aren't repeating. In this case, it's only my name, but I just split that up, so it's only going to be my first name and my last name. And so if I take this initial table on the top and I do both of my operations, I split up my domains and I copy my values, I end up in a table that contains the values as shown on the bottom. I also have to designate what my primary key will be, and in this case it's going to be last name, first name, course ID, and term. Yes, that has limitations, but for now we'll deal with it. Couldn't be just last name, first name, because I already have two values in there, and that would violate the duplicity constraint or the uniqueness constraint. So that's first normal form. Remove all the non-atomic domains, remove all the non-singular values, and you're good to move on. Again, it takes a judgment call to figure out which ones you do split up. In this case, I split up course in course ID and course name, but I did not split up the term in a year and say a season. That's a judgment call that I made. That was first normal form. The second normal form is something that only has to be checked when you're dealing with partial dependencies. So in other words, composite determinants. Let's read the definition first and then we'll go into more detail. The second normal form aims to remove partial functional dependencies, as I mentioned. Remember, the functional dependency means A determines B, so course number determines course name. What we're looking for is a composite determinant, where I may have a combination of two fields. So for example, course number and student number might determine grade. Now, if the course number determines the grade by itself, or the student number determines the grade by itself, then I have what is known as a partial dependency, and I want to get rid of those as much as I can. If I do need both fields together, then I have a complete or a full functional dependency. In the second normal form, if we want to formally define that, we want to say it is in the first normal form. In other words, if I don't have a confirmed 1NF situation, I can never have a second normal form. So first confirm that something is in 1NF, then find all of those non-primary key attributes that are not fully functionally dependent on the primary key. We want to get rid of those. It also means that if I don't have a composite primary key, I'm done. If I have a primary key that only consists of one field, by definition, if the thing is in 1NF, it's also in 2NF. Issues again is on functional decomposition. So if we were going to figure that out, we have to move all of those partial dependencies to a separate relation. Doing that would cause data loss, so we also have to establish a foreign key relationship. Let's look at the example. We have grades. I have last name, first name, course ID, course name, term, and grade. The primary key here is last name, first name, course ID, and term. So I do have a composite primary key, which means that I do need to check for second normal form. Now I could see here that the course name only depends on the course ID. It does not depend on any of the other fields that are part of the primary key. It doesn't depend on my last name, my first name, or the term. So that is a partial functional dependency, and I want to get rid of those. So that means I'm going to create a new table called courses. And in that I'm going to take my determinant and all of its dependents. So in this case only course ID and course name go into a new table. That means that all the dependents, so in this case only course name, can be removed from my original relation. And that means that that grades table is also updated to last first course ID, but then only with term and grade. We have course name removed from it because that was moved to a different relation. By itself, these two relations would now be lossy. I wouldn't necessarily know that the grade, the course ID in the grades table has to match the grade ID in the courses table. So then I'm going to put a foreign key relationship that begins in the grades table and that ends in the courses table. So that foreign key has to be defined. Otherwise I have lossful or lossy decomposition, and I don't want that. Without a foreign key, it would not be a correct answer. So now I have taken my one relation and I have created two smaller relations out of it. Looking at those again, courses is still in the first normal form. It's atomic domains and there's only one value each. Grades as well. And there are no more partial dependencies. Course name in the courses table only depends on course ID, and grade in the grades table depends on the combination of all four of the previous fields. So we're done for the second normal form. For the third normal form, we're going to remove transitive dependencies. And so that means if A determines C, and then C in its term determines B, that means that A transitively determines B, so indirectly determines B, and we want to get rid of those as well. Example will probably make it more clear. The definition means that a relation is said to be in the third normal form if it is in the second normal form. Again, if I cannot prove that a relation is in the second normal form, it can never be in the third. On top of that, I'm going to remove all of the non-primary key attributes that are transitively dependent, or in other words, I must ensure that all non-primary key attributes are non-transitively dependent on the primary key. So let's take a look at an example. Before we do that, how do we fix that? The same way, lossless decomposition. Not a whole lot of difference there in approach. Now, there are fourth and fifth normal forms. We are not covering those. There are other advanced forms of normalization. The one that we will look at is Boyce-Codd normal form. The higher order, so anything above the third normal form, could happen, but is mostly theoretical, and in practice you don't really run into those that often, so we're going to skip over those. Again, we are looking at Boyce-Codd normal form. And why is that? Well, Boyce-Codd normal form does not depend on any of the previous work we've done. You can go from unnormalized directly into a Boyce-Codd normal form. In practice, once you've arrived at the third normal form, in almost all situations you will also be in Boyce-Codd normal form. So it's often easier just to go from 1, 2, 3 and then check if you're in BCNF. The definition is that a relation is in Boyce-Codd normal form if and only if all determinants in the relation are candidate keys. That's all. That's the only thing you have to test for. And that sounds a lot simpler than all of those previous definitions. It turns out doing it turns out to be a whole lot harder. That additional do exist, but they're mostly theoretical. One point of caution: denormalization is a valid approach as well. But keep in mind that denormalizing is not the same thing as skipping normalizing. So why would you denormalize? In other words, purposefully introduce redundancy in your database. Now, one, it could be for maintaining history. Sometimes you want to be able to change things, and normalization might stand in the way of that. And secondly, and because everything is recorded only once, it means we have a lot of cross relationships between relations, and that does impose a computational overhead and adds complexity. So sometimes in order to increase query performance, we might denormalize as well. It is an optimization though, and optimization should only be engaged in if absolutely necessary. Don't optimize things that you don't have to optimize. Premature optimization is the root of all evil, as someone has said at one point. Optimization almost always adds complexity, and we try to remove and reduce complexity as much as we can. And that was the process of normalization. We covered the first, second, and third normal form, in which we removed non-atomic domains, repeating values. We removed partial dependencies and transitive dependencies, and we did that through the process of lossless decomposition. We do that in order to remove a redundancy as much as possible, even though we might reintroduce some redundancy for optimization purposes down the road. All of this sounds a little bit theoretical and abstract. That's why we'll practice with this in class, and you'll see what the consequences are of just starting somewhere and then actually going through the process to create an optimized database. That is it for now.